Good morning. This is a new section on ordered basis, assignment 1. The example is, let V be the vector space of all real polynomial of degree less than equal to n, together with the zero polynomial, over the field R. We have to prove that 1 plus x, 1 plus x whole square up to 1 plus x to the power n is a basis for V. Right? Now to prove the basis, we have to prove two things. That these number of polynomials, this set of polynomials should generate the vector space, and secondly, these should be linearly independent. Right? Instead of proving these two results for the basis, we are having one more result, that if V is a finite dimensional vector space and if the dimension of V is n or n plus 1, whatever dimension of V given to you, then the linearly independent subset consisting of n elements or n plus 1 elements, which is equal to the dimension of V, that forms the basis for V. So first of all, we have to prove that this is linearly independent, and because how many elements are present in this basis which we have to prove? Total number of elements are n plus 1, right? And dimension of V is, we will see that, okay? So if these two matches in number, then we say that these forms a basis for V. Alright, first of all, we know that standard basis for V is, I have already written this as a note. Standard basis of V is equal to 1 x, x square, x cube up to x to the power, and these are the standard basis for V. We all know this. So what is the dimension of V then? The number of polynomials present in the basis of V. How many polynomials are present? These are n and this 1, that is n plus 1 elements are there. So dimension of V is n plus 1, right? Okay. Now if you see that none of the polynomials, this 1 plus x, 1 plus x whole square up to so on, 1 plus x to the power n. None of these polynomials is a linear combinations of the preceding polynomial. So what can we say about this? These are then linearly independent. This is a result for linearly independent. If none of the polynomials is a linear combinations of the preceding ones, then those polynomials are linearly independent, or vectors or elements, right? So these polynomials are linearly independent because none of them is a linear combinations of the preceding polynomials. Now since, okay, now I'm using the result that if the dimension of V is equal to the number of elements or polynomials present in the linearly independent set, then that linearly independent set forms the basis for V. Now since dimension of V is n plus 1 and number of linearly independent polynomials is equal to how many? This is a linearly independent set. How many polynomials are there in this set? N plus 1. Okay. So these two are same in numbers, right? So therefore, this set is a basis for V, right? Okay. Let's move on to the second example. Let V be the vector space of all real polynomial of degree less than equal to n, together with a zero polynomial over the field R. Prove that 1 minus x. Now here the sign changes now. That doesn't matter. 1 minus x whole square up to 1 minus x to the power n. This is still a polynomial. This is a basis for V. Again, the same proof. What are the standard basis for V? 1 x, x square, x cube up to x to the power n. Because V is a vector space of real polynomials of degree less than equal to n. What is the dimension of V here then? Yes, n plus 1. So number of polynomials present in the standard basis of V is n plus 1. So the dimension of V is n plus 1. Now since none of the given polynomials, which we have to prove them as basis, none of the polynomials 1 minus x, 1 minus x whole square, so on, 1 minus x to the power n. None of these polynomials is a linear combinations of the preceding polynomials, right? Which means these polynomials are linearly independent. Now the dimension of V is n plus 1. Now in this linearly independent set, how many polynomials are present? N plus 1, which is same as the dimension of V. So these forms the basis. So the basis of V are this. So these are the bases for V. Fine. Alright. Let's move on to the other example. Under what conditions on the scalar B do the vectors 1, 1, 1 and 1b, b square forms the basis for R3? That is three-dimensional three-dimensional space. We know that the dimension of R3 is 3, right? Okay. So therefore, every basis of R3 will contain exactly 3 elements. What do you mean by the dimension? Dimension means the basis for that space must contain number of elements equal to 3. This is the result, right? So, now if the dimension of R3 is 3, then every basis of R3 will contain exactly 3 elements, which means for basis we require 3 elements. What they are asking, that vectors, first vector and second vector forms the basis of R3. How can they form the basis of R3? They are in only 2 in number. For the basis we should have 3 in number, right? So thus this set cannot be a basis for R3. Provided if 3 vectors are also given to us, that vectors first should be linearly independent, right? Then only they can form the basis for R3.